Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at the probability density functions and cumulative distribution functions for some common random variables. In fact, we're going to look at 3 random variable types. This is going to serve as an introduction only. This is going to be an introduction only. We're going to, in this video, we're going to look at three random variable types. There are others. There are many others in fact. And we'll encounter several of those other random variable types through the semester, and as we encounter them, I'll introduce them and tell you all of their properties. Random variables are most commonly described by their CDFs and their PDFs. Random variables are most commonly described by their cumulative distribution functions and probability density functions, and not the outcome to real number mapping function. Alright, so remember that a random variable is a function that maps outcomes to real numbers. Alright, we're not going to look at the random variable mapping function today. Random variables are most commonly described by their cumulative distribution function, or CDF, and their probability density function, or PDF. We're going to look at the PDFs and CDFs for 3 random variable types today. We'll come back and look at these random variables and others later on when we talk about means and moments and standard deviations and variances and all those other properties. We're not going to do that today. Today we're just going to look at CDFs and PDFs of some commonly encountered random variables. So the first one is going to be the uniform random variable. The uniform random variable. Alright, the probability density function for a uniform random variable looks something like this. Another way of writing the probability density function is using step functions. Okay, and the figure, the graph of a uniform random variable will look something like this. Okay, so a uniform random variable says that my value x is uniformly likely to lie anywhere between points A and point B. All right, so random variable x is equally likely or uniformly likely All right, so a uniform random variable is one that is uniformly likely to take on any value between two specified points, arbitrarily shown here as A and B. The amplitude, if you will, of my probability density function is chosen so that the area is exactly 1. Remember, one of the properties of a proper probability density function is that the area of the PDF has to be exactly 1. Okay? So what about the cumulative distribution function for a uniform uniform random variable? Let me draw the PDF one more time. All right. Now remember, the cumulative distribution function is the indefinite integral from minus infinity up to some unspecified point x of my probability density function. Okay? So what that means is we're going to start way over here, and we're going to integrate moving to the right and add up the area under my curve. This guy has unit area. So hopefully you would see then that my cumulative distribution function is going to look something like this. This will be point A. This will be point B down here. I know that below, to the left of x equals A, there's no area that's accumulated in my integral up here. And I know that cumulative distribution functions must approach 0 at minus infinity. So I'll just kind of draw this. This is meant to be 0. And I also know that as x approaches plus infinity, my cumulative distribution function must approach exactly 1. And after I've integrated all the way from A to B, I will have integrated the entire area under my probability density function, and so my integral must be exactly 1. And then, because of the nature of the uniform random variable, the area accumulates linearly from point A to point B as we integrate from the left to the right. That's the curve for my uniform random variable cumulative distribution function. I can write it down functionally as follows. It's clearly going to be 0 for x less than or equal to A. It's going to be a straight line, x minus A over B minus A. In the intermediate region, A less than or equal to x, less than or equal to B. And it's going to be 1 for x greater than or equal to B. Functionally, that's the way we would write down the cumulative distribution function for the uniform random variable. Okay? So that's it. The PDF, it just is sort of a squarish looking function with unit area there. And the cumulative distribution function is just a straight line starting at 0, going up to 1 linearly from points A up to point B. All right. The next random variable type that we're going to be interested in is the exponential random variable. Exponential random variable. The probability density function for an exponential random variable looks like this. All right, and the assumption here is that alpha is greater than 0. My PDF for the exponential random variable includes the step function. The step function means that my PDF has no value, or rather the value is 0 for x less than 0. So maybe we can extend this horizontal axis here. My PDF is 0 for x less than 0. Then it hops up to point alpha and decays exponentially from that point forward. And as usual, this is a proper probability density function. The area is 1 in all cases. All right. All right. All right. What about the cumulative distribution function? Cumulative distribution function is, recall, the indefinite integral from minus infinity up to some unspecified level, with the integrand being my probability density function. All right. Remember, the fundamental theorem of calculus tells us that the indefinite integral actually does have limits. The lower limit is minus infinity, and the upper limit is just an unspecified variable level. All right, so we plug our probability density function here into my integrand. The step function affects the lower limit, and I get an integral from 0 to x of alpha e to the minus alpha x dx. All right. We can continue with this. We get negative alpha over alpha e to the minus alpha x. Evaluate that from the endpoints 0 to x, and that gives me 1 minus e to the minus alpha x. All right, that's performing my integral. But then I have to add back in a step function. All right? That step function, this step function here, is not something that comes about because of the integration steps that I've done. This step function comes about because my cumulative distribution function begins at x equals 0. It has no value less than 0. All right? Be careful. Every now and then you're going to have to be on the watch for adding back in step functions. The step function in the PDF affected the lower limit on my integral here, but my cumulative distribution function is always and everywhere 0 for x less than 0, so I had to add it back at the end of the calculation. It doesn't come out of the integral itself, so please be aware of that. So then if we plot this, looks something like this. Cumulative distribution function always approaches 1 at x equals infinity. It's going to look something like that. Okay? It's going to be 0 at minus infinity, so my cumulative distribution function at minus infinity equals 0, as it's supposed to. My cumulative distribution function at plus infinity equals 1, as it's supposed to. It peaks out at 1, as it's supposed to, and it's an always non-decreasing function. The cumulative distribution function never decreases as a function of its argument, so it obeys all the proper properties. Okay? So, that's all I wanted to say today about the exponential random variable. Let's look at one final random variable type for today. And this one is called the Rayleigh distribution, or Rayleigh random variable. The Rayleigh random variable. We'll have quite a bit more to say about the Rayleigh random variable a little bit later on. In the next video, I'm going to introduce the Gaussian random variable. Later on in the semester, we're going to see that the Rayleigh random variable is related to the Gaussian. But that discussion will be deferred to much later in the semester. So anyhow, what does the probability density function for a Rayleigh random variable look like? Looks like this. That's supposed to be an a squared in the denominator of my exponent, and then a step function. All right, so my step function means that my probability density function PDF only exists for x greater than 0. All right. The piece out front is chosen so that the total area under my probability density function works out to be 1. So let's draw a picture of what the Rayleigh random variable PDF might look like. It starts off kind of steep, like this, and rolls over and decays. It's got a long decaying tail. All right. Turns out that the peak is at point A, and the maximum value is, you can plug in A in the PDF relationship, and you can see that the peak is 1 over A times the square root of E. As with all proper probability density functions, the area under my curve is exactly 1. It's unity. Okay, and you'll notice, just coincidentally by observation here, as my A parameter, as that A parameter in my PDF gets bigger, the peak gets smaller, peak gets smaller, and the curve itself peak gets smaller, but the curve itself gets wider, but the area remains unity. All right, so as the parameter little a gets larger and larger and larger, the peak will squat down, the curve will get wider. It always starts at x equals 0 and is 0 for x less than 0. But the area always remains 1, no matter what. All probability density functions have unit area regardless of the choice of variable parameters. Okay, what about the cumulative distribution function for the Rayleigh? Remind ourselves that the PDF is x over a squared e to the minus x squared over 2a squared u of x. And my cumulative distribution function is the indefinite integral of my PDF. And my step function affects the lower limit. So that gives me integral from 0 to x of x over a squared e to the minus x squared over 2a squared dx. Now I'm going to do a change of variables. I'm going to let u equal x squared over 2a squared, and du will therefore be x over a squared dx. All right. Use my change of variables and also have to change my limits. This gives me integral from 0 to x squared over 2a squared e to the minus u du, and that's negative e to the minus u evaluated from 0 to x squared over 2a squared, and this is 1 minus e to the negative x squared over 2a squared. And then, once again, I have to add back in a step function. All right, my Rayleigh random variable probability density function does not exist for x less than 0 by virtue of that step function. So at the end of my integral, I have to add back in that step function. This step function does not come out due to the integration process. It simply has to be added back in because the cumulative distribution function has no value for x less than 0. All right. So then we can sketch this. Cumulative distribution function peaks out at 1 and looks something like that. All right. The cumulative distribution function at plus infinity equals 1. The cumulative distribution function at minus infinity equals 0. It's an always non-decreasing function of its argument. It peaks out at unity, obeys all the proper properties of a cumulative distribution function. Okay, so that's our first 3 random variable types: uniform, exponential, and Rayleigh. We'll have a lot more to say about each of these random variables as we move through the semester. Later on, we'll talk about means and moments and variances and standard deviations and other things. And we'll introduce other random variable types as we get to them. In the next video, I'll talk about the Gaussian random variable at some length. But for now, That's all I've got for you today. As always, if you have any questions, please feel free to contact me at your earliest convenience, and I will answer all questions to the best of my abilities. Have a nice day. Bye-bye.